using paper on additional supply chain constraints, modules, and
Thanks for the introducing. Good afternoon, everyone. I'm Jing Yu from University of Alberta. On behalf of all the authors, today I'll present our paper, Optimization on Supply-Constrained Module Assembly Process. First, I'll start with the introduction part. Prefabrication and modularization have been widely used in the industrial construction projects, such as petroleum facility and the oil and gas plants. Prefabrication and modularization turn operations of a construction industry into lean production, while keeping the unique characteristic of each construction process. Here is the typical construction process for an industrial construction project in North America. Okay, the pipe spool fabrication and the structure steel fabrication are normally undertaken in the overseas vendor, such as South Korea and China, because of the lower labor cost and the convenient steel procurement. After finishing the prefabrication, these components are assembled into small modules in the overseas module assembly yard. After that, these small modules are transported from the overseas port to the local assembly yard for further assembly into larger modules, and finally for the on-site installation. These prefabricated spools and structure steel and small modules are called as engineered material. The logistics of this engineered material includes marine shipping, inland waterway shipping, and overland shipping. Okay, compared with the traditional bulk material, this engineered material has their own characteristic. As we all know, this bulk material are all raw materials, so they are massively manufactured and easy to procure. So they can be easily be available before construction. But for engineered materials, they are prefabricated based on the custom design. So they are difficult to fabricate and ship. Also, there is no substitute product or alternative vendors for this type of material. Therefore, for the industrial construction project, the engineered material is a driving factor for the construction planning and the resource scheduling. So the related literatures in the two areas, productivity study and lean construction, has also been reviewed. First, the productivity is a measurement of the overall effectiveness in converting labor efforts into useful outputs. So the focus of the productivity is the labor efforts and the equipment. While for lean construction, lean is a way to design production systems to minimize waste of materials, time, and efforts, and maximize the possible amount of value. The overall goal of lean construction is to remove non-value-adding activities. And one of its detailed objectives is to match the material supply and demand along this supply chain. And it's corresponding to related topics. One is the resource constraint scheduling, the other one is the supply chain management. So it is obvious for resource constraint scheduling, they assume the supply chain management can work properly, like to guarantee the materials are available when needed. But for supply chain management, they assume the resource constraint scheduling can tell them which materials is required at which time. So basically, these two topics are separate with each other. This setting is true for the bulk material, because the procurement and the shipping of a bulk material is of a lower uncertainty. So the just-in-time delivery method can be achieved with little inventory waste. So there is no need to integrate the supply chain and the construction planning. But for engineered material, it is different, because contract tends to deliver the engineered material at the earliest time, which will increase the inventory waste. And also the delivery process is of large uncertainty. So the delay of one certain engineered material may further increase the inventory waste of other materials which have already arrived on time or even earlier. So for industrial construction project, it is needed to integrate the information of material logistics and construction planning process to generate an optimal construction plan. So this paper focuses on the module assembly process in module yard because it is a middle stage between the module supply and the on-site installation. And the optimal assembly plan needs to mitigate the material idling waste. Here is measured by the total waiting time of overseas small modules. And the plan also needs to match with small module supply, satisfy resource availability limits, meet on-site demands. Okay, here comes to the methodology part. In this paper, a constrained program-based optimization framework is proposed. There are 4 elements in this framework: data source, extracted information, optimization engine, and outputs. Okay, first let's see the data source and extracted constraints. 3 data sources are involved in this framework: logistics management database, contract, and crew information. For the logistic management, it is used to determine the predicted arrival time for small modules, which are the hard constraints for starting the assembly. Okay, it means the large module need to be only can be started after all the small modules are available. The contract is to get the expected delivery time, which is the hard constraints for finished assemblies. Crew information is to get the crew limits, which are the hard constraints for executing assembly. Optimization engine. In this paper, constrained program is used to do the optimization work. And the optimization objective is to minimize the total waiting time, which is the inventory waste. And there are 2 outputs of this framework. One is the optimal assembly plan, which provides guidance for crew operation in module assembly yard. And the other one is the material waiting time, which is a basis for calculating additional material management cost. Okay, here's a case project to illustrate how the proposed method works. In this case, there are 10 large modules to be assembled from 40 small modules, and each one requires four small modules and have their own expected delivery time. The resource limits, 3 crews and 3 assembly bays are assigned to assemble these 10 modules. And 2 scenarios are assumed with different arrival time of each small module. The scenario 2 can be treated as an update of the first scenario, that some small modules are delayed due to some unexpected disruptions. Okay, here is the result. With the proposed framework, it can derive the detailed assembly plan for each scenario. So it means this proposed framework can provide the practitioner and support in deriving this assembly plan subject to dynamic logistic information. Okay, contribution. So for the academia contribution, this paper integrates the module supply information and the assembly plan. So it bridges the 2 research areas, which are productivity studies and supply chain management studies. And for the practical contribution, it integrates the material supply data and the project productivity data to generate the best crew job plan with the least inventory waste. So it can provide real-time decision support on construction plans subject to dynamic material supply information. Thanks for your time.
Thank you.